Hi kids, now we'll be going with this electrostatic revision. Okay, so going to the first question. So the question says like there is hemispherical shell and there is some point mass q, and okay, charge density of hemispherical shell is sigma. Now you need to find what is the force on this point charge. What is the force on this point charge? So by Newton's law I can say whatever force acting on this point charge will be same as force acting on this spherical shell. So I am going to find what is the force on the spherical shell. Now how I am going to find it is I will be taking some small element here, small element on the spherical shell, and I will be finding the force on that small element. So how much will be the force on that small element? That is field here because of this charge, which is kq by r square. Field times charge of this element. Charge of this element is sigma times dA. So this is the field of this charge into this charge. That will be the force acting on this small element. Force acting on this small element. So force acting on this small element is this much. So if I divide with the area, I will be getting pressure. So I know the pressure here, and I can see like forces are acting in the radial direction. So it's like pressure force, and you know how to deal with pressure forces. You have learnt in fluids. So instead of integrating, I can go with pressure times effective area. So pressure times effective area. Effective area will be like what will happen if you keep a torch here, what will be the shadow, what will be the area of the shadow, that is pi r square. So pressure times effective area, that will give me the force acting on the shell. But what was the question? The question was what was the force acting on this charge. So what we did, instead of finding the force acting on this charge, we found the force acting on this shell, so that we can avoid integration, because we used to do integration and we used to understand integration will yield a result in such a way that it is pressure times effective area, right? So now we know field because of hemispherical shell is sigma by 4 epsilon naught. So if someone asks you what is the field because of this quarter spherical shell, so field because of the quarter spherical shell will be symmetrically acting in this direction, which is at 45 degrees. So field because of this quarter will be making an angle 45 degrees with y-axis, 45 degrees with x-axis. But what will happen if I combine these two? If I combine these two quarters, what I will be getting? I will be getting one hemispherical shell. So that is the resultant of these two. And these two are perpendicular to each other. So the resultant will be how much? Root 2 into E. But what I know about root 2 into E? Root 2 into E is this much. So what about E? E is going to be sigma by 4 root 2 epsilon naught. So similarly, like I have taken simple example here, but you could have taken like solid sphere also. So if the charge of hollow hemisphere is Q, what is the potential at the center? That's easy to integrate also, but yeah, let me say if this charge is Q, now if this charge is Q, then the potential here is V. Then if I take other hemispherical shell, then the charge will be Q and this potential will be V. So if I combine these two, what I will be getting? I will be getting a hemispherical shell of charge 2Q. So what about the potential? Potential will be summation of these two. So V plus V will be equal to potential here. Potential here will be KQ by R. So what is V? V will be KQ by R. Now you may feel that for hemispherical shell it is quite easy to integrate. So maybe you could have taken the example of solid hemisphere, right? So going to the next one, it is finding the field on the axis of a uniformly charged ring. Now if you see here, there is a ring which was uniformly charged, and you want to find the field here at a distance x, where this radius is r, right? So assume like x is given, or assume alpha is given, whatever it is. So if this is x, this is r, this distance will be root of r square plus x square, and this derivation you must be knowing anyway. So if I want to find the field here, how much it will be? If I take some small element here, so then the field because of the charge will be kq by this distance square. K into that small charge by this distance square. But what I need, like when I want to sum up all those vectors, now this is the electric field because of that element. Now if you take all such elements, what will happen? They will be making a electric field vector will be making a kind of cone, or else if I resolve this vector into two components, one is x-axis and one is y-axis. Now when I take different elements, what will happen? All the electric field vectors will be like forming this way. So effectively this component will be getting cancelled. You need to add up only this component, or by symmetry you can say that electric field will exist only in this direction. So what I will be doing? I will be taking field because of this element and its component along horizontal, because I know this is the only thing which will be surviving finally. So I'll be integrating it kq by r square cos alpha and integration. Now all the things are constant. Cos alpha is same for whatever element you will be taking, and r square plus x square all are fixed values. So when I integrate, it is integral dq will turn out to be q, right? So it is same as, like, you will be getting the same result even if you keep just one charge here, one charge here. So if you keep symmetrically charges, you will be getting the same answer. It need not be ring, right? So finally what you will be getting? You will be getting, when you substitute cos alpha, you will be getting this much. Or what I can do, I can remember it this way. I can modify it this way, and I can remember it like kq by x square times cos cube alpha. Kq by x square times cos cube alpha. That way I can remember. And yeah, so I mean, yeah, fine. So what will happen when alpha tends to, okay, fine, leave it. So okay, so this is the result generally you will be remembering. So now what happens if x is much greater than r? If x is much greater than r, what will happen to the denominator? R square you can neglect, so x square whole power 3 by 2 will turn out to be x cube. So the result will turn out to be kq by x square form. Kq by x square form, that is, it is behaving like a point charge. That, yes, you can see what will happen if this x is very large. So effectively you will be feeling like this ring is like a point charge. The result also gives the same thing, right? Now we'll be doing it in the other way, we'll be deriving it in the other way. So we'll be finding the potential here, here how much it will be, like all the charges are at equal distance, so I can find the potential as k into dq by this distance, and I have to integrate. So when I integrate, I'll be getting k into q by that particular distance. So this is the potential due to ring at this position. Now I'll be seeing like what will happen if I move it slightly along this axis, that is, what will happen if I vary this x. So yeah, I'll be seeing like at what rate v is varying with respect to x. So when I do that, I'll be getting something, but I know electric field along this direction will be given by the rate at which, yeah, or else minus dou v by dou x, right? Minus dou v by dou x. If I want to find the electric field along this direction, I need to see how v is varying with respect to x, and I need to put minus sign. So this will give me electric field along this direction, which turned out to be something like this, right? So which is the same as previous answer, so you can get it in any way. Now we'll be trying to see like where it will become maximum. So for maximum, what we need to do, we need to differentiate it and make it equal to 0, right? So when will E dash become 0? When you differentiate it and when you make it equal to 0, you will be getting x equal to plus or minus r by root 2. So the meaning is maximum electric field will happen at a distance r by root 2, this side as well as this side. So when you try to plot the graph, it looks like, yeah, magnitude wise it looks like this, but if you want to see exactly, it's like if there is a ring here, now at r by root 2 it will be maximum and it will be in this direction. Here it will be maximum magnitude wise, but it will be in this direction if the ring is a positive charged ring, right? So maximum will happen at r by root 2. Now okay, so based on that we'll be solving this question. So in order to solve this question, all you need to know is for a ring, maximum field will happen at a distance r by root 2. So two equal point like positive charges A and B are symmetrical here. So it will produce a field like ring only on this axis, because their y components will be getting cancelled, only x component will be getting survived. What can you say for the net electrostatic force on a small electrically neutral rod placed on x-axis as shown in the figure? So now you need to understand there will be polarization happening. So it is a very small one. So if these are positive charges, what will happen on that small rod? What will happen? Yeah, this side, okay, if this is the small rod, this side charges will turn out to be negative, this side charges will turn out to be positive. So it's like, if these two are positive, what will happen? They will be attracting negative charge. So this side will become negative, this side will become positive, or you can try to understand like it will behave like a small dipole. If it will behave like a small dipole. Now whether it will be attracted or repelled or what is that? So they are asking like whether there is force acting or it will be force will be towards the origin or away from the origin, or information is insufficient. Now you can see the answer is information is insufficient. Now how you are going to do that is, now suppose if you you understood it will behave like a dipole where this side is a positive charge, this side is a negative charge. Now what will happen if I keep it? This is positive charge, this is negative charge. Now what will happen if I keep this positive charge exactly here and negative charge here? Now the force on the positive charge will be more than force on the negative charge, so it will try to go away. Now what will happen if I keep negative charge here and positive charge here? Then force on the negative charge is more, force on the positive charge is less, right? Force on the negative charge is more, force on the positive charge is less. So what will happen? It will be attracted. So information is insufficient. You need to know what is the location of the rod. So the next question goes like, we want to find the field because of a line charge at a distance x, where the length of the line charge is L, or yeah, fine, where the length of the line charge is L. Now what I am going to do is I am going to show you something which I know, maybe some of you might be knowing it already. So I need to find what is the field because of this line charge here at a distance x. This was the question. So what I will be doing, I will be taking some element here at a distance y. I am taking some element which is dy. At a distance y, I am taking some element which is dy. Now where this angle is theta. Now if this angle is theta, you can use this triangle and I can say y is x tan theta. I can take this triangle and I can say y is x tan theta. If y is x tan theta, by differentiating it I can say dy is x secant square theta d theta, x secant square theta d theta, right? Now I will be trying to find the field because of this one at this location, this element at this location. How much it will be? K into this charge by this distance square, Now it is K into lambda into dy, K into lambda into this charge is lambda divided, K into lambda into dy by this distance square. What is this distance square? X square plus y square, x square plus y square, x square plus y square. Now what I am doing here is dy, I am substituting it, which is x secant square theta d theta, and I am doing the modification. I am substituting like everything. Secant square, I just substituted the value. So when I did it, finally I ended up something like this, k into lambda x into d theta by x square, k into lambda x into d theta by x square. Now how I am going to look at it is, if there is a circular element, I mean if there is a circular charge, then if I take some element at an angle theta, that length is going to be how much? Okay, if this radius is x, then this element length is going to be x d theta. So the field because of this element, this circular element, is going to be how much? K into lambda into x d theta by this distance, which is x square. So that is, this is field because of the element on the circular charge. This is field because of the element on the line charge, which is, yeah, you can see the field because of this one and this one are going to be same. So what we can do from next time, if they ask you to find the field because of line charge, at a distance x, now draw a circle of radius x, and all you need to do is find the field from the circular element, but you must not find because of the total. You must find only till here, right? Till here, where the rod ends. So all you need to do is draw a line and see where the rod is ending, So if you want to find the field of the rod from here to here, you have to find the field because of the circular element from here to here. Now if you want to find the field because of the circular element, integration is going to be quite easy when compared to finding the field because of the line charge. Now as an example, you can solve what is your regular well-known question. So if there is a line charge of length 2L at a distance x, you have to find the field at a distance x. So what I can do, I will be drawing a circle of this much radius, and I will be seeing like where the end points of the rod are. So if I want to find the field because of this rod, I need to find the field because of this circular element. So basically this is the question, but I have converted it to this question. Now I want to find the field because of this circular element. Now by symmetry I can see because of that circular element the field will be along this direction. So what I will be doing, I will be taking some element from that circular part. So I will be finding the field because of that element, which is going to be how much? K into lambda x d theta by x square. But I know only horizontal component will be surviving, so I will be taking cos theta component, and I have to integrate from where to where. My theta varies from minus alpha to minus alpha to plus alpha. My theta varies from minus alpha to plus alpha. When I substitute the limits, yeah, sin alpha I know from the figure. When I substitute it, I will be getting something like this, which is well known result anyway. So that doesn't matter. So now you can see, like when x is much greater than L, again it will behave like a point charge. So the meaning is, if you want to find the field at a very large distance, this rod will behave like a point charge. So what is the takeaway from here? It's like if you want to find the field because of line charge, so you can convert it into finding field because of circular element. Now based on that, you can prove one thing. If there is a triangle made of three line charges, finite line charges, so you can show that in center will be the field at in center is going to be 0. The field at in center is going to be 0. So how I can do that is, if I want to find the field because of this element, this charge, I can convert the question into finding field because of this charge. If I want to find the field because of this charge, I can convert the question into finding field because of this charge. If I want to find the field because of this charge, I can convert the question into finding field because of this charge. But I know field because of this circular element is going to be 0 at the center, right? So field at the in center is going to be 0. So now the next question goes like, if there is a uniformly charged solid sphere, of course it has to be non-conductor. So yeah, volume charge density is rho. Now you have to find the field at a distance r. So what we will be doing, it is highly symmetrical, spherical, right? So I will be taking some spherical Gaussian surface of radius small r. So I will be writing integral E bar dot ds bar equal to q enclosed by epsilon naught, Gauss law. Now what I can do from here to here, by symmetry I can say no matter which area element I will be taking, field will be along the same direction. So dot product is going to be simple E into ds. That came because of symmetry. Now charge enclosed is density times volume of this element, which is 4 by 3 pi r cube, right? Now what about this? Again by symmetry I can say field at every point will be same, so I can take it out of integral. Now integral of all these areas is going to be how much? 4 pi r square. So from there you will be getting electric field is rho r by epsilon naught, magnitude wise. Direction wise you know it is going to be this direction. So if I want to put it in vector form, I can say field at inside point is going to be rho r bar by 3 epsilon naught. Now remember this result, because now I am going to solve 2-3 questions based on this result. Now you can see it is linear in r. So when it is linear in r, you might be getting like some really cool results. We'll look into one or two. So if there is a solid sphere, yeah, obviously like uniformly charged, but there is a cavity here. Now you have removed something. The only information given is density, and the distance between these two is, or this position vector is L bar. Now you have to find the field at point P inside the cavity. So what you can do, you can say the field in this structure at point P is nothing but the field because of the total sphere minus the field because of this sphere. So if I want to find the field at P, I can say it is the field because of the total thing minus field because of this thing. Now if I call this position vector as r1 bar and this position vector as r2 bar, it looks like this. So what will be the field because of this thing here? It is rho r1 bar by 3 epsilon naught. What will be the field because of this one here? Rho r2 bar by 3 epsilon naught. I have to subtract them. So what I will be getting? Rho by 3 epsilon naught into r1 bar minus r2 bar. But what you can see, this is r1 bar, this is r2 bar. So you need to find r1 bar minus r2 bar. So r1 bar, r2 bar, r1 bar minus r2 bar. R1 bar minus r2 bar is going to be L bar. So I can say it is going to be rho L bar by 3 epsilon naught. You can see it is uniform both in magnitude and direction. So field in the cavity is going to be uniform, which is same as at the center, so which is easy to calculate. From next time if you want to calculate, you can calculate for the center. That is going to be quite easy. So field will be uniform, that is in this direction again. It is in the direction of L bar, right? So field in the cavity is going to be uniform there. Now I am going to do some other thing. I am going to take some negatively charged solid sphere and positively charged solid sphere. now I am trying to do some kind of imaginary thing. So what will happen if I superimpose them? Negative and positive, when you superimpose, it will become neutral. So what I am doing is, I am almost moving their centers close to each other, very close to each other. So then it looks like this. It looks like this. So I am bringing this two together. So it looks like this. The only thing is, I am maintaining some small distance. Now you can see this entire thing will behave like a cavity. So it's like there is only charge here and charge here. So now, once it is behaving like a cavity, you know the field is going to be uniform. And it is going to be in this particular direction. Now, so field is going to be uniform in this kind of structure. Field is going to be uniform inside. But what about outside? Now, in this kind of structure, field inside is going to be uniform, because this question is same as the other question where the cavity is almost fully inside it. Right? So the field inside is going to be uniform, but what about the field outside? For the people outside, it behaves like, just if you are talking about point outside, this will behave like a point charge placed here, this will behave like a point charge placed here. So for people outside, how the effect will be? The effect will be like, there is positive charge here, there is negative charge here, or you will be feeling the effect of a dipole of length L bar, So inside the field is going to be uniform, but outside people will be going to feel it like a dipole of this much length. Now, if you want to find the charge density, like if this length is L bar, very small length, this length is going to be L bar, this length is going to be L bar, right? So if you want to find charge density at some angle theta, then I can say, if this length is L bar, this length I can easily prove like it is L cos theta, that you can do by yourself. So if I want to find the total charge here, it is going to be density times volume of that element. Volume is area times this length. Now, obviously, like it is not going to be volume charge density, so we have to see it like surface charge density. So if you want to see the same thing like surface charge density, it is going to be sigma into dA. So from here you can see sigma is going to be something like this, or it is of the form sigma equal to sigma naught cos theta. So charge density will be varying as a function of theta, or to be specific, it is varying at a function of cos theta. Now why I am stressing on this one is, why I am stressing on this one is, now you can see field is going to be uniform inside. So now if there is a neutral conductor, and if I apply electric field in this direction, uniform electric field in this direction, then what will happen? Charges will redistribute till the field inside will become zero. So the meaning is, if I apply some electric field in this direction, then the charges will redistribute and they will produce some uniform electric field in this direction, and they will be getting cancelled inside. So if I keep a conductor in a uniform electric field, charges will redistribute exactly in this manner. That is as a function of theta. It is not going to be uniform, it is going to be as a function of theta. Now if the charge distribution is in this manner, then the field because of those charges will be uniform inside, which is going to cancel the external electric field in case of conductor. Now, this is how the field lines will look like if the charge, with that charge density, inside field will be uniform, but for people outside it will behave like a dipole. Now, going to the next one. So there is a point charge here. There is an imaginary disk here where this angle is theta and this angle is theta to the extreme. So you have to find the flux through this imaginary disk. So what you will be doing, you will be taking some element here. So what I am doing here, I am taking some circular element because it is circular, is symmetrical there. So I will be taking some circular element at an angle alpha. This angle is going to be d alpha and stuff. So anyway, so the field because of this charge is going to be in this direction, but the area vector of this circle is going to be in this direction. Field is in this direction, but area vector is in this direction. They are making some angle. What is that angle? That angle is same as this angle, which is alpha. So if I want to find the flux through this element, what I need to do? I need to take the dot product of these two, which is E into dA into cos alpha. So E into dA into cos alpha. Now, what about things here? So electric field. Now if this is D, then this length is going to be D by cos theta. This length is going to be D by cos theta. So the electric field will turn out to be K into Q by that D by cos theta whole square. Now cos alpha will be, what is this? Okay, cos alpha I have kept it there. Now dA I have to find. Now how to find dA? Now that is 2 pi r. This circumference is, if this radius is r, then the circumference is 2 pi r and this thickness is dr. So area will turn out to be 2 pi r times dr. 2 pi r times dr. But what about this r? This r I can use this triangle and I can take tan alpha equal to r by d. So r equal to d tan alpha. So 2 pi r dr, where r is d tan alpha. So if r is d tan alpha, then dr will turn out to be d secant square alpha d alpha. Now anyway, I am not bothered about the integration, you must be knowing the result. So I am going to integrate it from where to where? From center to here, because then I will be getting all the rings. So 0 to theta. So when I integrate from 0 to theta, I will be getting the result like either this result or this result. So I will be remembering it by this way, because I can see this is the total flux. Out of the total flux, 1 minus cos theta by 2 is going through the imaginary disk. That you can check whether it is correct or not by keeping theta equal to 0 and theta equal to pi by 2 and stuff. Okay. So we can derive it by the other way also. Now we need to find the flux through this imaginary disk. So what I can do is I can visualize a sphere. Which encloses the disk just like this. So I can say flux through this disk, like flux through this, the number of field lines through this, between these two black dotted lines will be passing through disk and will be passing through this part of sphere. So I can say if I want to find the flux through this disk, I can say the flux will be same through this part of sphere. So what I will be doing is, now I will be taking that part of sphere and I will be taking some element. Now I need to find flux through this part of sphere, between the dotted lines, between the black dotted lines, right? Between the black dotted lines, I need to find the flux between this black dotted lines. So what I will be doing, I will be taking some circular element. Now you can see that is a sphere. So the area is going to be in this direction, right? So now I can see anyway. If I take some element, yeah, it is sphere now. So if I take any element on the sphere, the field and area vector is going to be in the same direction. Field and area vector will be going to be in the same direction. So E bar dot dA bar will turn out to be E into dA. E is KQ by R square, where R is the radius of the sphere. KQ by R square into area of this one. Area of this one is, yeah, so circumference times thickness. Thickness is R d alpha. What about radius? Radius is r sin alpha. 2 pi r sin alpha. 2 pi r sin alpha times d alpha. So this is going to be the area of that element. So electric field there times area. So which will turn out to be this much. So now you have to integrate. Now you can see this is going to be quite easy to derive. Like last time we got like many like big things in the equations, but here it is going to be little clean. So anyway, when you do the integration, you will be getting this result. Now I remember this result because I solve most of the questions based on this result. I get. So it's up to you. So if you feel the necessity, you can remember. But I think if it is coming more number of times, you have to remember it. So where I will be using it is, I will be showing one example here. Now there is a point charge here. There is a disk. This is an actual disk which is uniformly charged with the density sigma. Now the question is, I have to find what is the force on this charged disk because of this point mass. So what I can say, if I take some element here, the electric field will be in this direction, and I can see by symmetry or whatever it is, I can say the net force acting on this one will be going to be in this direction. So the meaning is I have to find only horizontal component and I have to integrate. So if I want to find the horizontal component of force, what I need to do, I need to take only horizontal component of electric field. So when I do that, what I will be getting? Force on that element is going to be sigma times area, which is going to be charge of that element times horizontal component of electric field. This will give me horizontal component of the force on that element. If I integrate, I will be getting the total force on the disk. So when I am integrating, what I can do, I can take sigma out because it is constant. Now Ex into dA is nothing but, what is Ex into dA integral? Which is nothing but flux, Now what is the flux? We have calculated flux is q by 2 epsilon naught into 1 minus cos theta. So this is the force acting on the disk. Now what I can say? I can say the force acting on the disk is same as force acting on the point mass. So I can say this is the same thing, force acting on the point mass. So I can modify, I can write the equation like I can bring the q this side and bring the remaining terms that side. So I can see it is of the form q into electric field because of the disk. So I can even get electric field because of disk at a distance, where the I mean in terms of angle I have, but yeah, so I can find, if they give me distance, I can find the angle, right? So I can even find what is the field because of the disk based on my flux derivation. So I'll be remembering flux result so that I can use it at many places. Now this one also you can try in the same way. So if there is a point charge and there is a square sheet of charge capital Q, so what will be the force on this square sheet? So again you can do the same thing, it is symmetrical, so the net force on the sheet will be in this direction. So all you need to do is find the force because of this vertical field. So that is sigma. If I take some small element, then the force on that small element in this direction is going to be sigma into A into dy. I can take sigma out, then it will turn out to be Ey into dA, which is nothing but dot product of electric field to area there, so which will turn out to be the flux. Now what is the flux through this square because of this point charge? Now if you want to calculate it directly, it is going to be hard, but what you will be doing, you can see this distance is d by 2, so you can make a cube. You can make a cube with this square plate. Where this charge will lie at the center. So if you can make a cube, and if this is lying at the center, then the flux through each face of the cube will be 1 by 6 q by epsilon naught. 1 by 6 q by epsilon naught, right? Now the next question goes like, the intensity of an electric field depends on the coordinates x and y as follows, where A is a constant, I cap, J cap are unit vectors, and x and y axis along with x and y axis. Find the charge within a sphere of radius r with center at origin. Now first of all you need to visualize how the field lines are going to be. It is going to be x I cap plus y j cap. So if this is y axis and this is x axis and this is z axis, then the field lines will be like radially. If this is z axis, then the field lines are going to be radial. So the field lines are going to be like this. The field lines are going to be radial. So this is the thing you need to understand. Once you understand that, it behaves like a line charge. So you need to understand the field lines will behave like field lines of line charge, not like point charge. But what they asked the flux through this sphere of radius r. This sphere of radius r. So what you can say, it is nothing but okay. So you want to find what is the charge enclosed in this one. Now how you are going to calculate it? Area is, now the field and areas are not going to be in the same direction. So we'll try to avoid too much integration and stuff. So what in Gauss law generally, like if they are asking question, most probably it's not about integration, it's about like avoiding integration. Now what I can do, instead of finding the flux through this thing, I'll be taking some cylindrical Gaussian surface of radius r and height 2r. Then I can say the flux through the sphere and the flux through that corresponding cylinder are going to be same. So the question is to find the flux through this sphere. Instead of that, I am going to find the flux through the cylinder. If I know the flux through the cylinder, I can say what is the charge inside. So electric field is given this way, I can modify it and I can write it like it is like the form distance, where r, root of r x square plus y square is r, right? So it is like of the form a by r into unit vector, So flux is going to be E into surface area. Flux will be only through that surface area of the cylinder, which is going to be 2 pi r times its length. Length is how much? 2r. E into 2 pi r times 2r. So this is the flux. If this is the flux, that flux I can say it is nothing but charge enclosed by epsilon naught. So charge enclosed is going to be 4 pi epsilon naught into A into R. The next question goes like, a bead of mass m and charge q can slide without friction on insulating thread tied between two diametrically opposite points on a ring of radius r made of insulating material. The amount q of positive charge which is uniformly distributed on the ring. Find the time period of oscillations of the bead about its equilibrium position. Mass of the bead is negligible compared to that of ring. So the meaning is, you need to assume like ring is not moving, so bead is moving. So this is the question. Now if you move the bead from the center in this direction, now you need to show that it will be performing oscillation. Obviously this is small distance, so it will be performing oscillation, and you need to find what is its time period. So for that, what we need to do, we need to find what is the field here because of this ring. So first of all, we need to find what is the field because of that ring. Thereafter we can multiply with the charge here to get the force, and it must be of the form, if this is x, then it will be of the form k into x form, right? So in order to find the field at point P, what I am going to do is, I am going to take some Gaussian surface like cylinder. Now I am trying to show the other view. So I have drawn a Gaussian surface like cylinder. Now where the radius of the cylinder is r, and this length is x, so this length is also x, so total length of the cylinder is x, 2x. But you need to understand all these are small, r is small and x is also small. I have drawn big just for you to understand it. Now what I can say is, through this Gaussian surface, there is no charge inside the Gaussian surface, so the total flux has to be 0. So when this is small, I can almost say like field, when that Gaussian surface is small, I can say field at every point on the curved surface is almost going to be same. So if this is positive charge, what will happen? The field lines will be going into the curved surface. So if the field lines are going into, then the flux is going to be negative. So the flux through the curved surface is going to be negative of electric field there times surface area. What is the surface area? Surface area is 2 pi r times this length, which is 2x. Now similarly, flux through this area and this area is going to be field there times that area, so that is EQ into pi r square. Again for this one also EQ into pi r square. So net flux has to be almost 0. I mean here these are not exact things, so we are approximating it to 0. So from here I will be getting what is the electric field at point P, that is electric field at point Q times something. Now how to find electric field at point Q? We already know the result, right? We will see what will happen when x is tending to 0. We can see the field is proportional to r. What is r? R is this distance, r is this distance. So field is going to be proportional to that distance r. So once you know field is this much, you know the force is this much, you know acceleration is this much, you can find time period, right? It is like SHM. So the next question is like, okay, this is not a question, it's kind of like, if there is a dipole at a distance x from origin, where this is minus q, this is plus q, and this is L bar, and the electric field here is E1, the electric field here is E2, then the force on this charge will be Q into E2, the force on this charge will be Q into E1 in this direction. So what is going to be the net force? Net force is going to be Q into E2 minus E1, or I can write it in vector form like this, Now the same thing like this. Now what is E2? E2 is electric field at x plus L. E2 is electric field at a distance x plus L. E1 is electric field at a distance x. So I can multiply and divide with L. And this L I can write it like x plus L minus x. Now when L is tending to 0, I can say this is nothing but dou E by dou x. So if there is a dipole placed in an electric field, what I can do? I can say the force on that dipole will be dipole times dou E by dou L. I mean how the electric field is varying along the direction of dipole, right? So if it is a uniform electric field, it is going to be 0. So the next thing is, if there is a charged sheet, of charge density sigma, and you know the electric field on this side of the charge density, this side of the sheet, which is E1 and making an angle theta 1, and you know the electric field here it is E2 and making an angle theta 2. So the information given is there is a sheet of charge density sigma, and you know the field on the right hand side is E1 making an angle theta 1, on the right hand side is E2 making an angle theta 2. Now this will be combination of field because of external field and field because of this sheet. This is combination of external field and field because of the sheet. So what I can do, first thing is I'll be resolving this into horizontal component and vertical component, which is E1 along normal and E1 along y-axis, E2 along normal and E2 along y-axis. But this is a combination of external field plus sheet. This is also combination of external field plus sheet. So external field, if I take it as this notation E, external field along normal plus external field along y, that will be remaining same that side also. So external field along normal, external field along y. Now apart from that, this is the combination of external field plus field because of the sheet. Field because of the sheet is going to be sigma by 2 epsilon naught. Field because of the sheet is going to be sigma by 2 epsilon naught. Now why I am doing all this stuff is I am trying to see what is the pressure that will be acting because of the external field. So the aim is to find what is the pressure acting on the sheet, right? So if I want to find the pressure acting on the sheet, what I need to find? I need to find this electric field. If I know this electric field, I can multiply with charge there and divide with the area to find the pressure, right? Or else I can multiply, all I need to do is find this one and multiply with sigma to get the pressure, right? So in order to get that, what I can say is, I can say E1 bar plus E2 bar, E1 bar plus E2 bar, E1 bar plus E2 bar is nothing but summation of these two vectors, Now when you add these two, what will happen? Sigma by 2 epsilon naught, sigma by 2 epsilon naught will get cancelled. So effectively you will be getting this E1, En and Ey 2 times. Or else I can say, when I add these two vectors, I will be getting effectively 2 times of external field. Or else E1 bar plus E2 bar by 2. This vector plus this vector by 2 will give me vector external field vector. Now similarly I need to find E2 bar minus E1 bar. If I do E2 bar minus E1 bar, what I will be getting? I will be getting 2 times of sigma by 2 epsilon naught. 2 times of sigma by 2 epsilon naught, which will be sigma by epsilon naught in this direction. So from here, if I multiply these two, what I will be getting? If I multiply these two, then I will be getting E bar times this one. Now both are in the same direction. Okay, or else E bar times n cap, or else I can say when I take the dot product, only this will be playing role. So E bar dot n cap will turn out to be E bar dot n cap will turn out to be E along that direction, which is En. So if sigma times of En by epsilon naught, will turn out to be this. Okay. So if I want to find this one, this is the pressure, right? This is charge per unit area times electric field because of the external source. Electric field because of the external source times what is the charge on unit area. This is the pressure. Now how I can write this one? This one I can write like sigma into n cap dot E cap. How I can find n cap dot E cap? By taking dot product here I can find. So when I do that, I will be getting half epsilon naught into E2 square minus E1 square, or half epsilon naught into E2 square minus half epsilon naught into E1 square. So if someone asks you what is the pressure on this sheet or on any element, all you need to do is you need to understand what is the field just beside this and what is the field just beside this. Net field. So once you know that, then you can say the net pressure is going to be half epsilon naught into E1 square minus half epsilon naught into E2 square. That is quite easy to remember because this term you must have seen somewhere, which is energy stored per unit volume. So, but we'll be deriving electrostatic pressure the other way generally, because that's not a straightforward method, right? This is not a straightforward method, what we know. So what is the straightforward method? We have to find the force on small element and divide with the area. So that will give me pressure. So for that, what I am going to do is, I am going to take some hemispherical shell. I will be finding electrostatic pressure for hemispherical shell generally. So you can do the same thing for any other situation also. So this is the traditional way what we follow. If there is a hemispherical shell and if you want to find the electrostatic pressure, So what you need to do, you need to take some element and small element, and you need to find the force on that, and you need to divide with that area. So in order to find the force on that small area, what I am going to do is, I am going to look at that structure like, I am going to look at this sphere like two parts. One is that small element plus one is the remaining part. So when I combine these two, I will be getting the total sphere. So what I will be doing now, my aim is to find what is the force on this element. What is the force on this element? Now I will do that, but before that, if I take this small element, a charge density sigma, in its surroundings, just beside this side, just this side, what will happen? It behaves like infinite sheet. So its field will be sigma by 2 epsilon naught and sigma by 2 epsilon naught. Just in the surroundings, the field because of this one is going to be sigma by 2 epsilon naught and sigma by 2 epsilon naught. Now, apart from that, what I know about the total structure? Inside the hemispherical shell, I know the field is going to be 0. Outside, I know it is going to be sigma by epsilon naught. I can take Gaussian surface and I can prove like inside flux is 0, so outside has to be sigma by, electric field has to be sigma by epsilon naught. So electric field at A is totally 0 and at B it has to be sigma by epsilon naught. But what I came to know at A it is sigma by 2 epsilon naught because of this one, at B it is sigma by 2 epsilon naught due to this small element. But what I know, if I want to find, if I combine these two, then I will be getting the field here as 0. Field at A has to be 0. Now how that can happen? Only when the field because of the remaining portion at A is going to be sigma by 2 epsilon naught. So if field because of this remaining portion is going to be sigma by 2 epsilon naught in this direction, it is going to cancel this sigma by 2 epsilon naught. So finally you will be getting 0. Now similarly, if at B the total field has to be how much? Sigma by epsilon naught. Now how you will be getting sigma by epsilon naught? Only when the remaining structure will be exerting electric field of sigma by 2 epsilon naught. So sigma by 2 epsilon naught plus sigma by 2 epsilon naught is going to be sigma by epsilon naught. Now what is the conclusion? The conclusion is at A as well as at B, field because of this remaining structure is going to be sigma by 2 epsilon naught. In fact continuous. The field is continuous, right? So if you know the field, then what you need to do? All you need to do is, if you want to find the force on this element, you have to multiply this field and this charge, right? So this charge is sigma times of A, that small area, and this field is sigma by 2 epsilon naught. So this is the force on that small element. If I divide with the area, I will be getting the pressure, sigma square by 2 epsilon naught. Now this is how we will be deriving for spherical shell or for any other structure if we are comfortable doing it. Now we already know something, which is, if you know the field on just this side and just that side, then you can use half epsilon naught into E2 square minus E1 square. Now what is electric field here? 0. Electric field here is sigma by epsilon naught. So I can substitute, one is 0, one is sigma by epsilon naught. I will be getting the same result. In a much quicker way. So whatever it is, if you want to understand the step-by-step way, or if you want to visualize, then break it into parts and find the force on that small element and divide with the area. If you directly want the answer, then you can directly go with this thing. A conducting shell, okay, fine. A conducting shell of radius r has charge q, electrostatic force between two parts of the shell which are on either sides of the plane, that is at a distance small r, which is less than r, from the center of the which are on either sides of the plane, that is at a distance r. Okay. So the thing is, there is a shell. Yeah, conducting or not conducting, it doesn't matter because it is a shell, like the charge will be uniform distribution. Now they are saying, like, if you imaginarily divide into two parts, one part and part 2, so they are asking what is the force on any one of this. So if I want to find the force on this, what I know electrostatic pressure on this one, right? Electrostatic pressure I know. So if I know electrostatic pressure, if I want to find the force, what I need to do, I can go with like my fluids analogy and I can say it is pressure times effective area. So it's like fluid analogy. So pressure times effective area, sigma square by 2 epsilon naught into effective area. Effective area will be, if I put a torch here, how the shadow will look like. Shadow's area will be this much, where this length is r and this length is capital R, so this length is going to be root of capital R square minus small r square. So pressure times effective area, that is going to be the answer. Right, so the next question is like, if there is a regular tetrahedral where the charges are q, 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 what is the potential energy of the system or mutual interaction energy of the system? It is like how many, you need to take one pair at a time and you need to find the energy of that pair, right? So how many pairs you can select? There are 4 charges, so you can select 4c2 pairs. So each pair potential energy is kq square by a. So that is going to be 6 kq square by a. The other way of looking at it is, if you take a charge and multiply with the potential there. Now what is the potential here? Kq by a plus kq by a plus kq by a. So potential here is kq by 3a. And if I multiply with this one, then I will be getting the energy there, right? So which is q into potential there, which is 3 times of kq by a. So what is this? This is the potential energy I am finding here for this one. So how many such charges are there? 4 charges are there. But what I am doing here, I am dividing with half. Only then I will be getting the required answer 6. Now why I am going to divide with half is, I am doing something like which is repeating the calculation. Now what is that is, if I am calculating q into v, so basically let me call this one as q1, q2, q3, q4. So then what I did here, if I don't divide with half, basically I am doing q1 v1 plus q2 v2 plus q3 v3 plus q4 v4. So basically I am doing this thing. But v1 includes potential because of 2, 3 and 4. v2 includes potential because of 1, 3 and 4. This includes 1, 2 and 4. This includes 1, 2 and 3. So you can see q1, q2, that is the pair, that is the interaction energy, right? Now here also q2 and q1, there is interaction energy between. So you are counting it twice. You are counting every pair twice. You are counting every pair twice. So if you are going by q into v method, you are going to count every pair twice. So you have to divide with half. So if you are getting confused with this, you just stick to your normal method. Now self energy of a uniformly charged hollow sphere. So what you will be doing? So you will be bringing charge from infinity and you will be imaginarily pasting it on the hollow sphere, right? So you will be bringing some small charge, pasting it. Again you will be bringing some small charge, pasting it. So at certain moment when the charge on the sphere is q, you will be bringing some small charge dq and you will be pasting on it. So what is the change in potential? It is kq by r. Yeah, that is potential times dq. So this is the work you are doing, right? So you are doing this much work. You are doing this much work. That is whatever charge you are bringing times what is the potential here. Then you have, that is the work done to bring the small charge. So if you want to calculate the total work done, then you have to integrate. You will be getting kq square by 2r. kq square by 2r. Now you see here we divided with half. Now that's the same reason we are getting half here. So potential due to the total charge is k times, if the total charge is capital Q, then the potential is k times of capital Q by r into whatever is the total charge is Q. But why we are getting half? Because we are counting every pair twice. Every pair twice. Anyway, so that's the self energy of hollow sphere. Now solid sphere self energy, what we will be doing? We will be bringing charge, we will be making some small sphere, thereafter we will be bringing some more charge and we will be increasing the radius. We will keep on doing that. So at certain moment when the radius is r, I am going to bring some small charge and I am going to paste some charge whose thickness is dr, right? So what is the work I have done now? That is potential there, which is k q by r, potential there times whatever charge I am bringing, that is this much, which is the charge of that element. Charge of that element is density times 4 pi r square dr. So this I have to integrate and stuff. When I integrate it and when I substitute, I will be getting the result as 3 by 5 kq square by r. This is the self energy of solid sphere, or this is the energy I have to spend to make it, right? So now what I am going to do is I am going to see the same thing, self energy of hollow sphere and solid sphere, in a different way. That is, wherever field exists there will be energy. So we are trying to see energy in terms of field. Now if there is a hollow sphere, I know field inside the hollow sphere is 0, so energy is not going to exist inside. I know field outside the hollow sphere is as if the entire thing is placed, the entire charge is placed at the center. So the field lines, if I imaginarily extend them, they will be meeting at the center, right? So now if I want to find what is the total energy existing outside, what I need to do, I need to take some small element and find the energy in that element, So I know half epsilon naught square is the energy in that energy in unit volume. So if I want to find the energy in this volume, I need to multiply half epsilon naught E square with that much volume dV, Now half epsilon naught E square at a distance smaller, electric field will be K into Q by distance from the center. So when you substitute this and when you integrate it, you can see you will be getting KQ square by 2R. So now what we did here, we just try to visualize, we are just confirming whatever we know is correct or not. Wherever there is energy, there will be electric field, and we know the relation is energy density will be given by half epsilon naught E square. So it turned out to be the same thing. So energy KQ, self energy of hollow sphere is KQ square by 2R, which is spreaded outside in terms of field. There is no energy existing inside. But what happens in case of solid sphere? In case of solid sphere, I can say there is field inside also, there is field outside also. But field outside solid sphere looks exactly same as field because of hollow sphere. Anyway, I am not going to do that. So I am dividing it into two parts. One is inside and one is outside. So I am trying to find what is the self energy inside. What is the energy existing in terms of field inside? What is the energy existing in terms of field outside? So what I will be doing, I will be taking some small element and I will be finding the energy in this element, which is half epsilon naught A square dV. Now electric field inside is this much. That you can refer from your notes if you want, or rho r by 3 epsilon naught we derived. Rho r by 3 epsilon naught, when I convert, it will turn out to be this much, right? So when you integrate, you will be getting 1 by 10 KQ square by R. Now what is this? This energy is energy from here to here, that is the energy stored inside the solid sphere. Now if I calculate the energy stored outside the solid sphere, it looks everything will go exactly same like what we did for hollow sphere, which will turn out to be KQ square by 2R. So for a solid sphere, energy existing outside is this much, energy existing inside is this much. What is the total energy? Total energy, when I add these two, I will be getting 3 by 5 KQ square by R, which is energy, self energy of solid sphere. So self energy of solid sphere is this much, but out of this, KQ square by 2R is existing outside and remaining is existing inside, right? So you can see energy in terms of field, that helps better. Now the extension of it is, if there is a small shell of radius r and charge q, uniformly distributed another shell, charge capital Q and radius is r. Now if you want to find the energy of the system, that is self energy of this one plus self energy of this one plus mutual interaction energy of this one. Self energy of this one is KQ square by 2 times of small r. Self energy of this one is KQ square times 2 by 2 times of capital R. Now mutual interaction energy, how to find? You can find either potential because of this one here and multiply with this charge, or you can find potential because of this one here and multiply with this charge. So potential because of this one here is K times of small q by capital R. K times of small q by capital R times the charge here. That is the mutual interaction energy. Now if you want to look at the same thing in terms of field, what I can say, this I can divide into 3 regions, region 1, region 2, region 3. In region 1, the field is 0. The field because of this one is going to be 0, field because of this one is going to be 0. So field in energy in region 1 is 0. So I want to calculate energy in region 2, energy in region 3. So I am going to do that. Yeah, you will be getting PDF, right? So you can do it by yourself. So when I do that, I will be getting this much. This is the energy stored in region 2. Now similarly, if I do for region 3, I will be getting this much. This is the energy stored in region 3. But if you look here, I have written in black color. Now what does black color represent? Every term in black color represent self energy of this one. So self energy of that one exists inside, exists in region 2. Yes, it exists in region 2 as well as it exists in region 3 also. Yes. Now apart from that, what about red color? Red color represents self energy of this sphere which exists in only region 3. Yes. Now what about this one? This is mutual interaction energy which exists in only region 3. Now anyway, when I add all these 3, what I will be getting? I will be getting this result, which is exactly same as this result. Now you see, in region 3, there are fields because of 2 charges, due to this one. So if you know in region 3 field is because of 2 charges, you can't just say like find the energy because of this one and find the energy because of this one and add. It's not going to be that way. The reason is, then the energy density is this much, so the energy is going to be into dV. So when you expand, you will be getting 3 terms. So if you know the field here is because of 2 fields, E1 and E2, then the energy doesn't consist 2 terms, energy consists 3 terms. That is, third one is going to be extra, which is mutual interaction energy, which we calculated and got something like this, right? Okay, going to the next question. Consider a cube as shown in figure 1 with uniformly distributed charge in its entire volume. Intensity of electric field at its vertex P is E0 and potential is V0. A portion of half size of the original cube is cut and removed as shown in figure. Find the electric field and potential of the new structure. So this was the old structure. Now they removed this part. So if they remove this part, they are asking what is the field there and what is the potential there. So what I can say I will find field because of this part, this entire thing, and I will find field because of this thing, and I will be subtracting. If I subtract, I will be getting the field because of needed structure, right? So similarly, potential also I will find because of this one, and I will find because of this small thing, and I will be subtracting. But for that, what I can see it is very highly symmetrical, and the field at point P, yeah, I think that you need to understand. That will be pointing from here to here, right? That will be along this line joining this to this, this to this. Now the same thing, field because of this small cube at point P is going to be along the same line. So field because of this big structure and field because of this small structure is going to be along the same line. So subtraction is going to be quite easy because they are going to be along the same line. Now I want to find how the field depends on the lengths. So by dimensional analysis, I know field must be of the form kq by r square. Kq by r square. There will be some numerical constant. That doesn't matter for me. That depends on whether it is center or corner or geometrical structure. Now geometrical structure is remaining same, so that numerical constant is going to be same. So if the electric field here is going to be E0, what is the electric field here due to that small structure is going to be? Now that's my question, right? So it must be proportional to q by r square. Q by r square. So it must be proportional to q by r square. But what about q? Charge. Charge, it is a cube. It has only one dimension. One length dimension, right? So that q must be proportional to a cube. That q must be proportional to a cube. So electric field is proportional to charge by a square, but the charge is proportional to a cube. So electric field is going to be proportional to a cube by a square. So electric field is going to be proportional to a. So yeah. So if the side length is 2a, whatever it is. Yeah. If the side length is 2a, then the electric field is E0. So if the side length becomes half, then the electric field will become half. So if I want to find the net electric field, I have to subtract these two, right? So E minus E0 by 2, which is going to be E0 by 2. And what is the direction? Direction is along the line joining these two. Now what about potential? Potential is a scalar quantity. Now going with the same logic, it's like potential dimensions must be of the form, potential must be proportional to q by a. Q by a. Again, q is proportional to a cube. So potential is proportional to a square. A square. So length square. So if the potential here is v, then the potential here will be v by 4. V by 4. Then the difference is going to be 3v0 by 4. Right? Now the next question goes in the same way but slightly different. A cube is made of an insulating material, has uniform charge distribution throughout its volume. Assuming potential due to this charge cube at infinity as 0, potential at the center is V0. So find the potential at its corners. So they said potential at the center, you need to find the potential at the corner given that potential at the center is V0. Potential at the center is V0. Now what I am calling is, I am assuming potential at the center for small cube. Potential at the center for a cube of side length A, I am calling it as, it must be of the form C1 KQ by A, where C1 is some numerical, or I can write the same thing as Q must be proportional to A cube. Q must be proportional to A cube. So A cube by A will turn out to be A square. So I will be saying potential at the center of a cube of side length A is going to be of the form S1 into A square, where S1 is going to be some value which is not changing, which is not going to change if it is center. Now by this logic I can say potential at the center of cube of side length 2a is going to be 4 times of s1 into a square or s1 into 2a whole square. Now similarly I'll be calling potential at the corner for a small cube of side length a as something like this. So that is s2 into a square from when I say like q must be proportional to a cube. Now by that logic I can say potential at the corner because of cube of side length 2a is going to be this much. Anyway, so these all things you can manage. Now the only thing what you need to understand is corner of one small cube, or center of one big cube. Center of one big cube is nothing but corner of 8 small cubes. Center of one big cube is corner of 8 small cubes. So that's the only thing. Center of one big cube is corner of 8 small cubes. So after that you will be getting the required answer. A uniformly charged rectangular triangular lamina ABC as shown in the figure. Acute angle A is theta. If the potential at vertices A and B are V and VB respectively, you need to find what is the potential at the center at the vertex C. So what they said, potential at A is VA. So where this angle is theta and opposite side is A, then the potential here is VA. So if the angle is 90 minus theta and the opposite side is B, then the potential here is going to be VB. Now they are asking what is the potential at C. What is the potential at C? So what I am going to do, I am going to drop a perpendicular. Now before that, potential must be of the form. What you have seen here, you have seen two triangles where you know one angle and opposite length. Kind of thing. So if I go with the same logic, if I know one angle and opposite length, then I can say V must be proportional to Q by R, but that Q must be obviously dependent on that length, right? Because that area must be depending on that length. So I can say Q must be proportional to R square, like sigma into R square, right? Sigma into area dimensions. So this is purely based on dimension analysis. From there I can say potential must be proportional to R. Now how we got this one? Because charge must be proportional to R square. So the first thing you need to understand is potential will be proportional to R, where R is the opposite length for me according to my logic, right? So now I can see two triangles. So I am going to concentrate on this triangle first and this triangle next. Now what about this triangle? I need to find potential at C. This triangle looks like triangle where this angle is theta and the opposite side is A sin theta. So that looks like similar to this one where this angle is theta and opposite side is A. So if this angle is theta and opposite side is A, then the potential is VA. If this angle is theta and this length is A sin theta, then that is going to be VA sin theta. That you can, by proportionality, it must be proportional to the length, right? So if this is VA, then this is going to be VA sin theta. Now similarly, if this is VB, where this angle is 90 minus theta and this side length is B, it is VB. So if the side length is B cos theta, then it is going to be VB cos theta. So potential due to this structure at C is going to be VA sin theta. Potential due to this structure at C is going to be VB cos theta. So totally it is VA sin theta plus VB cos theta. The next question goes like 2 point charges are there and equipotential surfaces are given. So what should be the separation between the charges, right? Now equipotential surfaces. Now I have broken that into two parts. So if I look at this part, then the field line must be perpendicular to equipotential surface if at all it is existing, right? So it must be perpendicular. Now similarly, if I take the other part, electric field must be perpendicular. But if you look at that intersection point, electric field can't be in two directions, right? Now electric field must be either along this direction or along this direction. But according to intersection, now if it is intersecting, then the electric field must be along this direction as well as this direction, which can't be possible. So the electric field is going to be zero there. Now what is the logic there? The logic is if two equipotential surfaces are meeting somewhere, then that is going to be null point or electric field is going to be zero. So once you understand the electric field is going to be zero, then you can solve the question much easily. Now the next question, consider non-conducting of radius r and mass m and particle both are resting. Okay, so I am not going to do that. You can try by yourself. So you can look from center of mass frame. So center of mass energy is not going to change. Only energy with respect to center of mass is can be useful to convert into kinetic energy. Kinetic energy you can break into two parts. One is kinetic energy of center of mass and one is about center of mass. Kinetic energy of center of mass is not going to change because no one is going to change the speed of center of mass here. All the forces are internal forces. So kinetic energy of center of mass is not going to be used as any other thing. So kinetic energy with respect to center of mass, initially it lies as kinetic energy. After some time it goes as potential energy and stuff. So we will be looking from center of mass frame. From ground frame it looks like this. From center of mass frame it looks like this. Now if the kinetic energy with respect to center of mass is just sufficient enough so that they will be coming on to the same point, onto one point, and they will be stopping. Now sometimes what can happen, the given energy is less, so that they can't even come to the same point. So the meaning is both will be having u by 2, they will be coming, they will be reducing their speed, they will be stopping. Now because of repulsion again they will be going back. So the ring and the point charge are never going to cross in this condition. Now what about the third condition? Like they will be crossing. So if they are crossing, what will happen? Like after crossing, because of repulsion, this will be increasing its speed. Again it will be going to this side, the point charge is going to be that side. But again both are equal masses, so finally when they are going to infinity, the speeds have to be going to be u by 2, right? That you can manage. Now potential on the rim of the disk. So I want to find the potential at point P. If I want to find the potential at point P, what I am going to do, I am going to take some sector here, and I will be trying to find the potential because of this sector here, and I will add all such sectors. But again, finding potential due to sector is not so easy for me, so the sector also I will be breaking into small areas. So this element, I will be trying to find the potential because of this element, and I will add all such elements to get potential because of sector. Now I will be adding all such sectors. So if this length is r, this length is going to be dr, and if this angle is theta, this angle is going to be d theta. So this length is going to be r d theta. So what is the area of this element? R d theta times dr. So what is the potential because of this element here? It is k times of charge by r. That is the potential because of this element. Now if I want to find because of sector, what I need to do? I need to integrate from where to where? Small r is 0. Small r is 0 here. Now small r is how much? That is 2r. Now you can see this right angle triangle. 2r, 2 capital R cos theta. So small r varies from 0 to 2 capital R cos theta. Now remember one thing, while doing this integration, theta is not varying. So you can treat theta as a constant during that integration. So due to that strip or sector, I found potential is this much. So potential due to this strip at point P is going to be this much. Now if I want to find potential because of all such strips, what I need to do? I need to integrate from theta equal to minus pi by 2 to plus pi by 2. When I integrate it, I will be getting sigma r by pi epsilon naught, right? Now the next question also you can try by yourself. So it's about everything tries to attain stability, that is potential energy minimum. So there are n drops here. So n drops, they will be having electrostatic self energy, electrostatic potential energy, at the same time surface tension energy. So the total energy has to be minimum. So for total energy to be minimum, its differentiation has to be 0. So when you do that, you will be getting the required answer. Going to conductors. Now suppose this is the thing. Now suppose this conductor is extending to infinity. This conductor is extending to infinity, and there is a cavity here. So this is the conductor and it is extending to infinity, and there is a cavity here. Now the thing is, nothing is placed in the cavity. Now I am going to see how the charges will be. For that, how the charges will be redistributed. Now for that, I have taken two Gaussian surfaces. One is here, one is here. One is including the cavity, one is just in the material of the conductor. Now first I will be concentrating on this one. So if I concentrate on this one, that is in the conductor. In electrostatics, in the conductor, field is 0. Because if the field is not 0, then the free electrons will be moving. Then it is not electrostatic situation. So in electrostatic situation, free electrons are not moving. Not in a regular movement. So the meaning is field has to be 0. So field has to be 0 inside the conductor. So if field is 0, if I take some Gaussian surface, if I take some small area here, flux through that Gaussian surface is 0 because field is 0. So field is 0, so flux is 0, flux is 0, flux is 0, flux is 0. So I can say total flux through this Gaussian surface is 0. If the total flux through the Gaussian surface is 0, then the charge enclosed must be 0. The charge enclosed must be 0. So from there what we can conclude, if there is a conductor and in the material of the conductor there won't be any charge by this logic in electrostatics, right? So that material of the conductor, or sometimes we call it as meat of the conductor. So in the material of the conductor or in the meat of the conductor in electrostatic situation, field is 0. From there I can use Gauss law and I can conclude charge in the meat of the conductor is 0. Now going to the other part, in this part again I have taken Gaussian surface and I know this is in the meat of the conductor. So in the meat of the conductor I know field has to be 0 in electrostatic situation. If the field is 0, then the flux through that area will be 0. So flux through any small area is going to be 0. So flux through the total area is going to be 0. If the flux through the total area is going to be 0, then the total charge enclosed must be 0. Total charge enclosed must be 0. Right? So but total charge enclosed 0, does that mean like no charge will be available, or like some positive charges and negative charges will be induced? Let us see that. So total charge enclosed is 0. Can this happen? Can this happen like there can be positive charge induced this side and negative charge induced this side, so that the electric field lines will be going from positive to negative charge, and obviously they must be coming at an angle 90 degrees and they must be ending at an angle 90 degrees because conductor is going to be equipotential surface, right? If it is not equipotential surface, charges will be under movement, but we know it is electrostatic situation, charges must not be under movement, right? So by the same logic I can say in electrostatic situation field lines must enter at perpendicular, right? Perpendicular. Now the thing is, can this be possible? Now I am going to show like this is not going to be possible. Now how I am going to show it is, now I will be taking some line, electric field line, or I'll be taking some charge, some unit charge via this path. Now that was field line earlier, but now I am going to take something via this path, some point charge. Now when I am taking from here to here, electric field is doing positive work, right? If I take positive charge, electric field is doing positive work. From here to here, electric field is doing no work because electric field is 0. So from here to here it is doing positive work, from here to here it is doing 0 work. So in a loop electric field is going to do positive work, but we know electrostatic force is a conservative force, so work done in closed loop has to be 0, but in this particular case it is not going to be 0. The meaning is this situation can't exist. So what we can conclude? We can conclude the total charge, I have taken Gaussian surface, I concluded flux is 0, so total charge enclosed must be 0. If the total charge enclosed is 0, there can be this situation possible we thought, but we concluded this is also not possible. So what will happen? It just looks like this. There won't be any charge. Now we will see what will happen if we keep some charge in the cavity. So now I have taken some irregular shape, but still it is extending to infinity. There is conductor which is extending to infinity. Now, okay, just follow my step by step things. Now I am placing some charge Q here. Now I am going to take some Gaussian surface, and by the same logic electric field has to be 0. So the flux has to be 0. So the total charge enclosed is 0. So if this charge is plus Q, then this charge has to be minus Q. But what we know about the conductor is already, I didn't give any charge to the conductor initially, so the total charge has to be 0 for the conductor. So from where this minus Q came? This came from the outer surface. So outer surface has to be positive charge for the conductor, because we know in the material of the conductor or in the meat of the conductor there is no charge going to be existing. So what are the step by step things? We have taken some Gaussian surface and we concluded flux is 0, so total charge enclosed must be 0, so this has to be minus Q. So if this is minus Q, then outer surface charge has to be plus Q. So these are the things we concluded. Now we will talk about something here. We will talk about point A. Now point A is in the material of the conductor or in the meat of the conductor. So in the meat of the conductor field is going to be 0. So at point A In fact, at point B also, in fact, any point, no matter which point you take here, field has to be 0. Field has to be 0. Total field has to be 0. Now the total field there will be because of 3 charges. One is this one is this one, the other one is plus q, which is at very far distance, which is at infinity. So electric field at A is 0. Electric field at A is 0, and electric field at A because of plus q. Electric field at A because of plus q is also 0, because plus q is at very far distance, so its field will be 0 at A. Similarly, electric field at B is also totally 0, and because of this charge is also 0, because it is at very far distance. So from there what I can conclude, electric field everywhere is 0, and field because of this one is going to be 0, so field because of this combination has to be 0. So what I can conclude from here is electric field at A is 0. Now that electric field, I can say it is combination of electric field because of, I have put in colors, electric field because of this red color charge and this blue color charge and this green color charge is going to be 0. But out of these 3 terms, I concluded this green color charge has to be 0 because it is at very far distance. So if this is going to be 0, then what I can say, summation of these 2 is going to be 0. Summation of these 2 is going to be 0. So in order to put that as a result, what I can say is, I can divide it into 2 parts. One is like inside the cavity, one is outside the thing, outside the conductor. So field because of all the charges inside this, field because of all the charges inside the cavity is going to be 0 anywhere outside the cavity, and field because of this outside charges is going to be 0 inside the conductor. So how we concluded that, we have taken point A and we understood at point A field because of this q is 0. So field because of these 2 has to be 0, because we know total field at A is 0. So we have taken A, field at A is totally 0, and field at A because of this plus q is also 0. So field at A because of this combination has to be 0. Now the same logic we applied for B also. Field at B has to be 0. Field at B because of this charge has to be 0. So field at B because of this pair has to be 0. So if field at A because of this pair is 0 and field at B because of this pair is 0, I can easily conclude myself that field because of this pair has to be 0 everywhere. Now what is the thing I concluded? I concluded a field because of this pair is going to be 0 everywhere. I can even convince you field because of this one is also going to be 0 everywhere inside the conductor. Now how I am going to do that is, I start removing the material. If I start removing the material, this size is going to be reduced. This plus q is going to come closer. Going to come closer. But what we know, we already know field because of these 2 is 0. Field because of these 2 is 0 in the conductor. But we know total field also is 0. Total field is also 0. So if you start shrinking it, what will happen? Charge will redistribute in such a way that field because of that outside charge is going to be 0 inside. Or like if you don't want logic, you can just remember it. Field because of this inside charges is going to be 0 anywhere outside this region. Field because of this all outside charges is going to be 0 anywhere inside it. Right? So yes, I have taken Gaussian surface. I concluded flux is 0. So total charge enclosed must be 0. There is plus q placed here, so there must be induced charge minus q. Yes, now I will be going with one example where we will be including almost all the things. So okay, now I am going with some example where I try to include almost all the cases. It's like there is a spherical conductor and there are 3 cavities. And listen to step by step things what I am going to say. I have placed some q1 at the center of this cavity and q2 somewhere here, and this cavity I didn't place any charge, but I placed some charge q3 here. Now what I am going to do, I am going to take some Gaussian surface here, that is in the meat of the conductor. In the meat of the conductor, electric field is 0, so flux through that Gaussian surface is going to be 0. If the flux is 0 through the Gaussian surface, then the total charge enclosed must be 0, so there is already q1, so the inner induced charge has to be minus q1. But you can see this is placed at the center, so by symmetry this will be uniformly distributed charge minus q1, or I can say it looks like a shell. It looks like a shell of uniform charge distribution minus Q1. Now if I go with the same logic, if I take the Gaussian surface here, in the meet of the conductor, flux is field in the meet of the conductor is 0, so flux is 0, so total charge enclosed must be 0. So if this is Q2, then this will be minus Q2. But what about the charge distribution? It is not going to be uniform because it is not placed at the center. So it is placed close to this surface. So more negative induced charge will be here and less negative induced charge, whatever it is. It won't be uniform. It will be non-uniform. Here Q1 is uniform charge distribution, minus Q1 is uniform charge distribution, minus Q2 is non-uniform charge distribution. Now, what happens? From where this minus Q1 and minus Q2 came? Conductor was neutral initially, so total charge on the conductor must be 0. Minus Q1 came here, minus Q1 came here, minus Q2 came here. So the charge on the outside thing has to be Q1 plus Q2. Now, if there was no Q3 available here, then it would have been uniformly distributed. This Q1 plus Q2 would have been uniformly distributed because field because of these two is 0 anywhere outside, so it won't be feeling any effect of this. So if it is not feeling any effect of this, it will be just distributing in such a way that how it naturally goes, like uniform distribution. Now similarly, field because of this one also is 0 anywhere outside, so it won't be experiencing any force because of this one also. So it will be uniformly distributed if this Q3 is not there. Now what happens if you bring Q3? That uniform distribution will be like modified like till when the charges will move in such a way that the field inside the conductor has to be 0. So everything happens till the field inside the conductor is 0, right? So now the field inside the conductor, inside the conductor in the sense in the meet of the conductor, in the material of the conductor. So whatever in electrostatic situation, field in the material of the conductor is 0, right? Now we look at some points. We look at point C. So we will try to find field at point C and potential at point C. Field at point C and potential at point C. Now field because of this pair, field because of this pair anywhere outside this region, field because of this pair anywhere outside this region is going to be 0. So C is outside this region, so field at C because of this pair is going to be 0. Similarly, field because of this pair anywhere outside this region is going to be 0. So field because of this pair at C is going to be 0. Now field because of this pair, this outside charges Q3 and this thing, field because of that pair is going to be 0 inside the meet of the conductor, and C is not only meet of the conductor, it's just this border. So anywhere inside this border, field because of this Q3 and this outside charge is going to be 0. So field because of this pair is going to be 0, field because of this pair is going to be 0, field because of this pair is going to be 0 at C. Now what about the potential? Field because of this pair is going to be 0 here, right? Now forget everything, now assume like there is only this pair. So because of this pair, field here is 0, here is 0, here is 0, here is 0, anywhere it is 0. So potential here, everywhere it is same, which is same as potential at infinity, that is 0. So field because of this pair is 0 everywhere outside. So potential because of this pair has to be same everywhere outside, which is same as potential at infinity, which is 0. So effectively what I can say, if I want to find something outside this cavity, I don't have to bother about this because it is not producing any effect in field, neither producing any effect in potential also. So if I want to find something here, something outside this region, then I don't have to bother about this because it is not producing field as well as potential. So field because of this one is 0 at C as well as potential is also 0. Now going by the same logic, field because of this pair is 0 anywhere outside. Now potential because of this pair will be same anywhere outside, which is same as at infinity. So field because of this pair is going to be 0 here, potential is also going to be 0 here. But what about this pair? Field because of this pair, now forget remaining things, just look at only these two. Now field because of these two is going to be 0 anywhere inside. Field because of these two is going to be 0 anywhere inside this region. So field because of these two is going to be 0 here. So field because of these two is going to be 0. But what about the potential? potential field because of these two is going to be 0 everywhere inside. So potential because of these two is going to be same everywhere inside. That much we can say, but we can't say it is 0. So I can say field because of these two is going to be 0 inside. So potential because of these two is going to be same everywhere inside. But out of all inside points, this is some good point where I can calculate the potential actually if I know this distance and this distance. So if I know this distance, okay, let me call this as R3 to C. Okay, R3C. So then the potential because of this one will be KQ3 by R3C. Potential because of this outer charge is going to be K into total charge by this radius. Now understand that even though if it is non-uniform distribution, I can say all the charges are at equal distance to the center. So potential calculation is going to be easy at the center. Even if it is non-uniform distribution, I can clearly say potential at the center because of this outside Q1 plus Q2 is K into Q1 plus Q2 by this radius. So conclusion, field because of pair Q1 and minus Q1 is going to be 0 at C. Field because of pair Q2 and minus Q2 is also going to be 0 at C. Field because of pair Q3 and Q1 plus Q2 is also going to be 0 at C. Totally it is 0, obviously, like conductor, in the meter of the conductor field has to be 0. But what we know? We understood potential because of this pair is also going to be 0 at C. Potential because of this pair is also going to be 0 at C. But potential because of this pair is going to be same everywhere inside, which is same as C, which is easy to calculate at C, which is KQ3 by R3C plus K into Q1 plus Q2 by R. Now going to other point A, somewhere here, point A. Now field because of this pair is going to be 0 anywhere outside. So field because of this pair is going to be 0 here, as well as we concluded that potential is also going to be 0. So field because of this one is going to be 0, potential because of this one is going to be 0. Field because of this one is going to be 0, potential because of this one is going to be 0. Field because of this pair is going to be 0, but potential because of this pair is going to be constant everywhere. Field because of these two is 0 everywhere here. So potential because of these two is going to be same everywhere here. But it is difficult to calculate here. Even though you know this distance, potential calculation because of this charge is going to be difficult because it is non-uniform distribution. But what is the logic? The logic is field because of this pair is going to be 0 everywhere inside. So potential because of this pair is going to be same everywhere inside, which is easy to calculate at C. So I can say potential at A is same as potential at C if I consider only these two charges, right? So going with the conclusion, field because of this pair Q1 and Q2 is 0, potential is also 0. Field because of Q2 pair is also 0, potential is also 0. Now field because of this outside charges pair is also 0, but potential at A is difficult to calculate. But what we know, potential everywhere inside because of these two charges is going to be same. So instead of finding potential at A because of these two charges, I will find potential at C because of those two charges. So instead of finding potential at A, I will be find potential at C, which we have calculated already. Now going to point B, somewhere here. Now that is outside this region. So field because of this pair is going to be 0. Field because of this pair is also going to be 0. Potential because of this pair is going to be 0. Potential because of this pair is going to be 0. Now what about the other one? Field because of this pair is going to be 0 anywhere inside it. So field because of this pair is going to be 0 at B. So if the field because of this pair is going to be 0 everywhere inside, then the potential because of this pair is going to be same everywhere inside. But this point is not symmetrical, so finding potential because of this charge is going to be complicated. So what I will be doing, I know potential everywhere has to be same inside because of these two charges. So instead of finding potential at B, I will find potential at C. Field because of these two charges is going to be 0 everywhere inside. So potential has to be same everywhere inside. So potential at B will be same as potential at C. So potential due to this pair, field because of this pair is 0, potential because of that pair is 0. Field because of this pair is 0, potential because of that pair is 0. Field because of this pair is 0, but potential at B is difficult to calculate, but I know potential at B must be same as potential at C. Now going to the next point is D, somewhere here. Now this is inside this cavity, so I will come to this cavity later. First of all, let me discuss field because of this one. Now field because of this one anywhere outside this is going to be 0. Now D is outside that, so field because of this pair is going to be 0 here. Field because of this pair is going to be 0. Potential because of this pair is going to be 0. Now what about this one? Field because of this pair is 0 anywhere inside this. Field because of this pair is going to be 0 anywhere inside this. Now D is inside this. So field because of this pair is going to be 0 at D. Field because of this pair is going to be 0 at D. So if I want to find the potential at D, it is hard for me because this charge is non-uniform distributed. So, but what I can say, field because of these two charges is 0 everywhere inside, so potential everywhere has to be same. So potential at D will be same as potential at C. I can calculate potential at C easily because even though if it is non-uniform distribution, every charge will be at equal distance from center. So I can find field and potential because of this one easily, field and potential because of this one easily. Now I will go and find field and potential because of this thing. Now field because of this charge will be in this direction, which will be kq1 by this distance square. Kq1 by this distance square. Now what about field because of this charge? That charge is uniformly distributed like a spherical shell. So what will be the field inside the spherical shell, which is uniformly distributed charge? Field will be 0. So field because of this q1 will be kq1 by distance square. Field because of this minus q1 is going to be 0. And potential because of this charge is going to be kq1 by this distance, and potential because of spherical shell everywhere will be same, which is same at the center, which is going to be kq1 by this radius r1 minus kq1 by that radius r1. So I have done this one first. So field because of this pair is 0 and potential is also 0. Field because of this pair is 0, potential is difficult to calculate at D, so I will be calculating at C and I will be saying both are equal. Now coming to this point, field because of this q1 is going to be kq1 by the distance square. Field because of minus q1 is going to be 0 because it is uniform shell. Now what about the potential because of this one? It is going to be this much. Potential because of minus q1 is going to be minus kq1 by r1, where r1 is the radius. So if you want to find the potential because of this charge at D, you can't find, but you know it is uniformly charged shell kind of thing. So potential everywhere because of that charge will be same. So you can calculate, inside. So you can calculate at the center easily, right? So going to the next point. The next point is E somewhere here. Now this E is inside this cavity. So I will come to this pair later. So first of all, let me conclude about this one. Field because of this pair anywhere outside has to be 0. So it is 0 here. Potential because of this pair everywhere has to be same outside, which is same as infinity, so that is 0. So field because of these two is 0 at E, and potential because of this pair is also 0 at E. Now coming to this point, coming to this pair, field because of this pair is 0 everywhere inside, so E lies inside, so field here is 0 because of these two charges. Now potential because of these two charges is same everywhere inside, so I know how to calculate at C, so I can say potential at E is same as potential at C, right? Now going to these charges, now field at E because of this q2 will be kq2 by this distance square, kq2 by this distance square. Now field because of this negative charge, now we can't calculate field because of that negative charge easily. We need to know the charge redistribution, we need to know the distances, and it's going to be complicated. All I can say is it need not be 0. Field here need not be 0 because of this inner charge distribution. This is uniform charge distribution, this is non-uniform charge distribution. So there is something different happening from previous case, right? So field, if the field because of this one, okay, the field because of this one is going to be in this direction, I can't particularly calculate field because of this one. So when I put it here, field because of q1 pair is going to be 0, potential is also going to be 0. Now outside charges field is 0, potential will be same as center. Now there is a complexity happening here. Field because of q2 is going to be kq2 by this distance square, and field because of this one I can't easily calculate, but it need not be 0 like uniform distribution case. So potential at this point is kq2 by this distance. And what about potential? Potential won't be equal to 0 because all the charges are negative, so it will be negative. Potential will be negative, but I don't know how to calculate the value, right? Now there is a point F outside. Now I'll be again breaking into 3 pairs, first pair, second pair, third pair. Field because of this pair is 0 everywhere outside, F is also outside, so field because of this pair is 0 here. Potential is also 0 because of this pair. Now field because of this pair is also 0 anywhere outside, so field here is 0 because of this pair, so as well as potential. Field because of this one is 0, potential because of this one is 0, field because of this one is 0, potential because of this one is 0. Now what about this one? Field because of this one will be kq3 by this distance square. Field because of this one I can't calculate easily. If it was uniform distribution, I could have assumed placing at the center. As it is non-uniform distribution, I can calculate it easily, but all I can say is it won't be 0. So field because of first pair is 0, potential is also 0. Field because of second pair is 0, potential is also 0. Now field because of third pair, I can't calculate summation, so all I know is I can calculate this one easily. Calculation because of this one is difficult. Now potential calculation also. Potential calculation of this one is easy, but due to this one is going to be difficult. Right? So the next question goes like, an electrostatic potential V has been measured everywhere outside and it is like uniform charge distribution, like A by R form. So what can you conclude? Will it be like uniform distribution, symmetry and stuff? So I think you can try that by yourself. So all I have to say is, if there is a conductor where this charge is placed anywhere, like symmetrically or not, it is a cavity, so you place anywhere. If this charge is Q, this charge will be minus Q, that you can get by Gauss Law, right? So if the charge is minus Q, then the outside charge distribution will be plus Q, and it will be uniform charge distribution outside. So if it is uniform charge distribution outside, then the potential will be varying of the form inversely proportional to R, right? So if I have a non-conductor, where I can stick the charges, I'll be sticking the charges in the non-conductor exactly like this. If I stick the charges like this, then the net effect because of all these charges will behave like there is only this charge, like the potential will be inversely varying with R. So this is one of the example I can give. Maybe you can find other examples by yourself, right? But you can't conclude anything just by knowing the potential outside. You can't conclude the charge redistribution just by knowing the potential outside. So the next question goes like, there is a point charge here, there is a spherical conductor here. So you need to find what is the potential of the conductor. So what will happen? Charge redistribution will happen. Negative charges will accumulate here, positive charges will accumulate here, and the field lines will look something like this. They will be ending at perpendicularly. They must be ending perpendicular, and here from positive charge they will be coming out perpendicularly, whatever it is. So you want to find the potential of the conductor. Now for the first thing is, conductor, every point on the conductor will be at same potential. If they are not at same potential, then there will be field existing, so the charges will be moving, but we know it is electrostatic situation. So in electrostatic situation, potential of the conductor must be same at every point. So no matter which point I take in the conductor, field has to be 0, or it must be equipotential. So potential at everywhere A, B, C is same. A, B, C and O will be same, but finding potential at A or B or C is difficult because it is non-uniform distribution, but finding potential at O is going to be easy because this distance is R given, and even though it is non-uniform distribution, I can easily calculate the potential because of this charge, that will be K into total charge by radius. Total charge is 0, so potential because of this charge is going to be 0 here, potential because of this charge is going to be KQ by R. So potential at O is going to be KQ by R. So potential everywhere inside will be going to be KQ by R. Now the next question, there are two small conducting spheres. So what I have given is, I had some charge capital Q, I have given to them and I just joined them by a wire. So, and the distance is very large when compared to the radius. So what will happen? Charges will redistribute till this one will get some Q1 charge, this one will get some Q2 charge. So what will be the ratio of those charges? Now that's the question. So I know Q1 plus Q2 must be equal to capital Q. So this much I know. Now I think if I differentiate, I will be getting this one. Anyway, I will be using these things later. So I didn't do anything other than like charge conservation there. Now till when the charges will get redistributed, till their potential energy will become minimum, because every system will try to achieve stability, that is potential energy is minimum. So let me calculate potential energy. Self energy of this one is this much, self energy of this one is this much, mutual interaction energy of this pair is going to be this much. So now this potential energy has to be minimum. If the potential energy has to be minimum, then the first differentiation has to be 0. So when I make the first differentiation 0, I will be ending up with some result like this. This term must be equal to this term. Now if I try to look from the figure, this term is going to be kq by r1 plus kq2 by l2. So kq1 by r1 plus kq2 by l2 is nothing but potential of this sphere approximately. Now what about this term kq2 by r2, kq2 by r2 plus kq1 by l, which is potential here, kq2 by r2, kq1 by l. So charges will redistribute such that their potential energy will be minimum. So when you try to solve it, you will understand that potential energy minimum case is nothing but when their potentials will become same. When their potentials will become same. So you can solve from there, like from these equations. Yeah, if L is much greater, then you can say like these two will be almost equal, and you know this condition, and you can do everything. Now the next question is, this is the conductor, there is a small hole here, you placed a point charge here and you are moving it. How much work you need to do to move it out to infinity through this hole? So if I keep it here, I can take Gaussian surface here, I can conclude the inner induced charge is minus q and it is uniform distribution. If inner induced charge is minus q, this outer induced charge will be plus q. So the field lines will be like this emerging, and there won't be any field lines here, there will be field lines emerging outside like this, because this is uniform charge distribution. So the field lines, if you extend them, they must be meeting at the center. So this is how the field lines look initially. Now when I take it outside to infinity, how the field lines will look? Now there won't be any field lines here, I have taken to infinity, so there will be field existing everywhere here. Now what is the difference from this figure to this figure? The difference from this figure to this figure is, in this region field was not existing earlier, now there is field existing in this region also. So if I calculate what is the energy existing in this region, that is going to be half epsilon naught e square into dv integration. When I do that, I will be getting this much. So what happened? Initially there was energy missing here, but that energy appeared here. So that energy came from somewhere, from where it must have come. I have done some work which has been converted into that potential energy or field energy. Now capacitors, if there are two conducting plates placed close to each other, and if I have given q1 and q2 this, how the charges will be redistributed, right? So we can easily understand the field will be uniform when you place them close to each other. So I'll be assuming that the field lines will be parallel. Right? So I'll be taking some Gaussian surface where one area is inside the conducting material, and this field, that's curved surface, right? So flux through this area is 0 because field is 0. Flux through this region is 0 because field is 0. Now flux through this curved surface is going to be 0 because field lines are along the surface. So the total flux is 0. If the total flux is 0, then the total charge enclosed must be 0. So the meaning is, if this side attains plus x charge, then this side attains minus x charge, right? So I am assuming this is y and this is z. This side charge is y and this side charge is z, right? But what I know y plus x has to be q1 and z minus x has to be q2, conservation of charge. Now apart from that, what I know, field in the meet of the conductor has to be 0. So if the field here has to be 0, then the field here because of y, x, minus x and z has to be 0. You can easily see field here because of x is going to be in this direction. Field because of this minus x is going to be in this direction, and they will be equal and opposite, so it will be 0. So field because of this pair is going to be 0 here. So if the field because of these two have to be 0, field because of this y will be in this direction, field because of this z will be in this direction. Now how much is the field? Sigma by 2 epsilon naught, or sigma by 2 epsilon naught. So anyway, that you can conclude, sigma by 2 epsilon naught, y by a by 2 epsilon naught, z by a by 2 epsilon naught. So y by a by 2 epsilon naught in this direction, z by a by 2 epsilon naught in this direction, they have to be equal. When they will be equal? When y is equal to z. So I can conclude outside charges must be equal. So I can conclude y must be equal to z. From how I got this? By making field equal to 0 in the meet of the conductor. Now what about this? Y plus z is q1 plus q2. How I got this? Total charge, that is y plus x minus x plus z. The total charge here must be same as total charge here. So I got this one by charge conservation. So there are two equations, I can solve for them, and I can get y equal to z equal to q1 plus q2 by 2. So y equal to z equal to q1 plus q2 by 2, q1 plus q2 by 2. But what was the total charge? q1. So out of q1, this much went here. So the remaining, that is q1 minus this thing, will appear here. So out of q2, something went here. So q2 minus this thing will appear here. Now this is for two plates. Now I can generalize it for many plates also. I can go with the same logic. If there are many plates and charge given is q1, q2, q3, q4, q5, q6. So if this is plus a minus a, I can go with Gauss Law, right? Sorry, this instead of x and a and b, you can take x and y. Instead of a and b, take x and y, because I have used a and b here. So if this is a minus a, this is b minus b, c minus c, d minus d, e minus c. And I know, you can take this as x, this as y. So x plus a is q1, this plus this is q2 and stuff. So that much you know. And summation of all the charges, that is x plus 0 plus 0 plus 0 plus 0 plus 0 plus y. So that is x plus y must be equal to summation of all these charges. So x plus y must be equal to summation of all those charges. Now I can take field in the material of the conductor is 0 anywhere. So if I take the field in the material of the conductor is 0, field because of this pair is 0, this pair is 0, this pair is 0, 0, 0. Field because of this one is going to be this direction, field because of this one is going to be this direction. Now they will be equal in magnitude only when their charges are same, that is x equal to y. X equal to y. So x plus y is this much, x equal to y. So x equal to y equal to half of total charge. So when I generalize it, what is the conclusion I got? No matter how many conductors are there in this kind of situation, outside plates will be having equal charges, and how much they will be equal to? They will be equal to half of the total charge. So to make it as an example, I have taken the same thing. The charge here is 12 units, 12 units, 12, 6, 6, 6. So total charge is 54. Out of 54, half will appear here 27, half will appear here 27. Now if this is 27, out of 12, 27 came here, so remaining will appear here. If this is minus 15, this will be plus 15. So 15, there is 12. So if this is 15 and the total available is 12, this has to be minus 3. If this is minus 3, this will be plus 3. Out of plus 3, out of 12, plus 3 came here, so remaining will be plus 9. If this is plus 9, this will be minus 9. If this is minus 9, total available is 6. So out of if this is minus 9, this has to be 15. If this is 15, this is minus 15. Total charge is 6, so this has to be plus 21. If this is plus 21, this is minus 21. You can see 27 minus 21 is going to be 6. So whatever we have done is right. So this is how you can solve numerical questions. It's going to be much simpler. Now, if there is a question like this, if there are 4 capacitor plates and there is a battery connected here and there are wires joined here. So if you want to find the capacitance of the system, now you can take this distance as d, and area as a and stuff, equal distance. So one thing is battery will give net 0 charge. Effectively battery will be giving 0 charge. So you know if there are 4 conductors and the total charge given is 0, so outside charges will become 0, right? Going with this logic. Outside charge will be half of total charge given. Now what is the total charge given? 0. So outside charges will become 0. So after concluding this, what I am doing is, I am taking this potential as V, this potential as 0, this potential as A. If this potential is A, it is connected by a wire, so this potential is also A. Now I am assuming, this is higher potential, right? So I am assuming this as plus X, this as minus X. So these two I assumed, plus X and minus X. So if I assume this as plus X, then this will be minus X. This will be minus X. If I assume this as plus Y, then this is minus Y. Now if this is minus X, it is joined to this one. So this has to be plus X. The reason is total charge on these two plates initially was 0. So finally also it has to be 0. There is no way the charge can go. Charge can only flow from this one to this one and this one to this one. But it can't go from here to somewhere. So total charge on this one plus this one must be same as initial, which is 0. So if this is minus X, this will be plus X. So if this is plus X, this has to be minus X. This has to be minus X. Now you can see there are 3 capacitors kind of thing. This capacitor has a charge X, like X and minus X. This capacitor has charge Y and minus Y. This capacitor has charge minus X and plus X, right? So I can say, I can redraw the figure. Like I can see 3 capacitors. One capacitor is between 0 and V. The other capacitor is between V and A. The other one is between 0 and A. So one capacitor is between V and 0, which is in green color here. The other one is between V and A, which is in red color. The other one is between 0 and A, which is in blue color. Now you can see these two are in series. So C by 2 in parallel with C, so 3C by 2. So effective capacitance will be this much. Now this is how you will be like modifying and doing, but without modifying still we can do it. Now I'll be doing the same thing. Now I have taken this picture here. I have taken the same picture here. Now what I am going to do is I am trying to find the potential difference between V and A while going from this side. From here to here I will be finding potential difference between V and A from here to here. So from here to here potential difference between V and A is X by C. From here to here it is V by C plus minus X by C. So potential difference between V and A from here to here is this much. From here to here is this much plus this much, right? Now apart from that, what I know, potential difference between these two is V. So I can say, yeah, I can apply for this one also, that is this. What is this? This is the potential difference between these two, which is Y equal to CV. Y equal to CV. Now from here I can solve and I will be getting 2x equal to y equal to CV. But what I need effective capacitance. The meaning is total charge given by the battery, that is x plus y, q equal to CV. So C equal to q by V. So x plus y by V. So I can substitute it and I can get the required answer as 3/2C. Right. So the next question is, there is a capacitor which was charged initially to capacitance is C1, charged with the potential V1. So plus the charge will be plus C1 V1 minus C1 V1. There was other capacitor charged to plus C2 V2 minus, yeah, charge is C2 V2. The meaning is positive charge is plus C2 V2. Right. So now what I am doing, I am taking these capacitor plates and I am joining their positive terminals and their negative terminals. So what will happen? Charges will redistribute till their potential difference will become same, right? So let me say the new potential difference is V. So charge on this one will be C1V, charge on this one will be minus C1V, charge on this one will be C2V, charge on this one will be minus C2V. But what I can say these two plates are connected, so summation of these two charges will be same before and after, like isolated plates. So there is no way charge can go from these two plates to anywhere. So C1V plus C2V will be same as C1V1 plus C2V2. So C1V1 plus C2V2 equal to C1 plus C2 into V. How I got this? Charge conservation. Now what about the initial potential energy stored in this one? Half C1V1 square. In this one half C2V2 square. So final energy is, I can say, this potential difference is V, this potential difference is V. So half C1V square, half C2V square, or half C1 plus C2 into V square. So final energy is this much. Sorry. Yeah, I must have taken modulus of this. It is like initial energy will be more. So you can do it. So heat will be modulus of this, which is initial energy minus final energy. So when you do that, you will be getting heat energy. I mean the difference in the potential energy will go as heat energy, which will be half C1 C2 by C1 plus C2 into V1 minus V2 whole square. This looks exactly same as half into M1 M2 by M1 plus M2 into V relative square. You can see why it is, because this equation looks like this, like momentum conservation in perfectly inelastic collision. Now again here this term has to be here, this term has to be here, like initial kinetic energy will be more. So this term looks like this term looks like this term. So the equations look same, so the result also has to look the same, right? Okay, a parallel plate capacitor of capacitance of voltage V. Okay, I think you can read the question. I will be explaining like what it is. The total charge is Q. Now what you are doing is you are removing the battery and you have placed dielectric. When you have placed dielectric, the charges will redistribute in such a way that to maintain this two potential differences, yeah, this entire thing at same potential and this entire thing at one single potential, or the potential difference to remain same, right? So what they said is, in this region the charge became Q by 2, and in this small region, this area is A by 3 only, this area is 2A by 3. So in this total region the charge is Q by 2, so in this total region the charge is minus Q by 2. Now the important thing is outside charges will be 0. I am not bothered about, okay, because the total charge given by the battery will be 0. So this charge is Q by 2, this charge is minus Q by 2, they said. And so where the remaining Q by 2 went? Remaining Q by 2 must have come into this region. Now that region I have put it in red dots. Now that region consists of two layers. One is plate layer. Plate layer will have charge Q by 2 because Q by 2 went here. Remaining Q by 2 will come onto this plate. But not only this charge. Now because of this polarization will happen and the dielectric surface will have some other negative charge. Now I am going to call it as minus q. Now if this is minus q, then this dielectric surface is going to have minus plus small q, and this is q by 2, so this has to be minus q by 2. So out of q, q by 2 went here, q by 2 went here, because of this polarization happened, and minus q came here, So what is the total charge inside this dotted line? That is q by 2 minus small q, right? Now if the potential difference has to remain same, then the field here and field here has to remain same, right? So what is the field here? Field here is sigma by epsilon naught. Now this field must be same as field here, which is sigma here by epsilon naught. Not only that, they have given some dielectric constant. The meaning is the new field is 1 by k times of what would have been the field if dielectric was not there in this region. Now if I take this one separately, if I remove dielectric, what will happen? There will be q by 2, there will be minus q by 2. So what will be the field if there was no dielectric? It will be sigma by epsilon naught. But when I keep dielectric, what will happen? The field will become 1 by k times. So I can say field here is equal to field here, and apart from that, field here is 1 by k times of what the field would have been if dielectric was not there. Now I can solve from here, and I can get k equal to 2, q equal to q by 4. So once I get the result, I can put it in the figure. So out of total q by 2 went here, because of this polarization happened, minus q came here. So the total charge, including the charge on the plate and polarized, is plus q by 4, and this is minus q by 4. Now they are asking to find the force between this plate and this plate, not the effective force, this plate and this plate. So you need to find the field because of this charge and multiply with this charge. So field because of the charge is sigma by 2 epsilon naught into charge. Now similarly, field here because of this plate is this much into the charge. So the total, anyway, these two are not equal, so you can eliminate option C, and when you add that, you will be getting option D, right? So charges will redistribute such a way that the potential difference will be remaining same, right? So this question you can try by yourself. I will be just saying like what it is. They said like when electric field is applied in this direction, then the charge on this one is going to be q1 and charge on this one is going to be q2. By symmetry, you can say charge on this one is going to be q2. Now if I apply the field this way, now it's like rotating this figure by 90 degrees. So charge on this one is going to be q2, q1. Now if I rotate it 90 degrees, or if I rotate it further 90 degrees, then the electric field will be in this direction, q2, q1. If I rotate it 90 degrees, then the field will be in this direction, q1, q2. Now, now I understood how the charges will be depending on the field direction on those particular rods. Now what happens if I apply field in this direction? Field in these rods are q2, and this one it is q1. But if I apply field in this direction, it is q2, and q1. So if I apply field in the opposite direction, then this is going to be minus q2, minus q1. So if I combine these two figures, or if I keep the field in this direction, then this is minus q2, minus q1. Then if I club these two figures, then I will be getting this one. So if I apply electric field, I will be getting minus q2, minus q1 from here, and from the above figure q2, and q1. So similarly, I can club these two above figures, and I will be getting this one. Now if I club these two figures, then I will be getting minus q2, minus q1 and stuff, right? So but what happened here? Here electric field in this direction is E, in this direction is E, so resultant is root 2E. Root 2E is the electric field, but in the question they said what happens if you apply electric field E here. So if I have to apply electric field E, then I have to make this one E by root 2, E by root 2, E by root 2, E by root 2. So when I make electric field 1 by root 2, then all the charges will become 1 by root 2, right? Thank you.